Test? Yes? No?
Hey, Francois.
Good?
Okay. Okay, I'm going to get started here. Hi, everyone. I'm Pete. I'm one of Russ's graduate students, and Lucas is sitting up here. And we're both going to give a lecture today. I'm going to give the first half. Lucas is going to give the second. So today we're going to talk about manipulation, which if you don't know what that means, it's robots moving stuff. And a little bit of context, just want to mention that Russ does actually now have an entire class on manipulation. He just started it last year. It's offered in the fall. I'm pretty sure it's going to be offered again in the fall. That's 6881. And it's a cool new class. Today's lecture, though, is going to be about the view of robot manipulation from the lens of underactuated robotics. And just kind of a brief intro. So, in this class, you guys have been learning a lot of very useful stuff. And a lot of it is very, very fundamental and is not going to change anytime soon. And then you've also been learning about very state-of-the-art techniques that I think are also very, very lasting contributions in the research field. This is a very strong foundation. And I do want to go through the next handful of slides some problems in robotics for which this toolbox that you've been learning is very directly applicable. And then we're going to talk about robot manipulation and how our toolbox can apply there. So let's first remind ourselves, hopefully you guys know a few of these things. Do you guys know what dynamic programming is? I think you covered that in class. So yeah, let's think about our toolbox. One thing we've got dynamic programming. Another one we have is stability analysis via SAS, sums of square programming. And then definitely a big hammer is trajectory optimization. These are very generally useful tools for lots of different problems. So let's think about, though, when are these tools applicable and when are they not applicable? When can we use them and when can we not use them? Does anybody know what's a key assumption that we need to have in order to make discretized dynamic programming work?
We have to have some degree of smoothness.
Probably some smoothness, yes. I'm not 100% sure on the technical condition, but I would imagine that would probably need to be the case. There's a big one, though, that I'm thinking about if we're going to discretize the space and do dynamic programming. Yep.
Low dimensional action space?
Yes, definitely. Definitely the dimensionality needs to be reasonably small. So I would say is the key one. We also, though, let's just look at the equations we have. We need to know what our cost is. We need to know C. We need to know F, which is the dynamics. And then we need to know X, which is our state. And we also need to know U, which is our control input. So we always basically assume those things are known, but we do need to know those. How about for SAS? So the key one there is F needs to be a vector-valued polynomial. And it actually turns out that a lot of very useful systems can be written down as vector-valued polynomials, but that is the key assumption there. In terms of dimensionality, I've seen as high as 70 been handled with SAS. I'm not sure if that's the exact limit, but that's the highest that I've seen. How about trajectory optimization? What is a key assumption about using trajectory optimization? Anybody?
Have to know X.
Have to know X, that's a good one.
If it's very nonlinear, I guess you can't do like a finite. You have to do a finite horizon stuff. It seems like if it's high dimensionality, you can't do just like from here to a goal. You can do sort of like at this time steps, the next time step, this time steps, the next time steps, like linearization. I don't know what that means.
I think that's a good set of thoughts. For me, the biggest one is that trajectory optimization will always give you local solutions. So you're going to have some initial guess, and then, so if I'm a quad rotor and I'm trying to fly around a tree, if my initial guess was to go right around the tree, I'm never going to like just jump through the tree and decide to go left. So for me, that's the big assumption about when we use trajectory optimization. We're going to only have a local solution, locally optimal solution. So those are good things to keep in mind. And again, we need to know C, which is the cost function, and we need to know F, which is the dynamics. So controlling the pendulum, dynamic programming works great, right? Because the state space is 2, dynamic programming is super happy, works very well there. It's beautiful, the solutions that can come up with. How about verifying a plane is stable? So I actually have heard through friends people that at like very big companies, very seriously sending planes all over the world using SOS to do stability analysis for planes flying in low angle of attack regimes. Here's a very cool one. Landing a SpaceX rocket. How do you think you might do this? I mean, come on, it's just awesome. So I have heard through the grapevine that they do use trajectory optimization as kind of the key. I mean, there's of course there's a whole ton of awesome engineering that goes into that. But in terms of actually coming up with a trajectory to hit zero velocity when you hit Earth, that's a trajectory optimization problem. So just to write this down, fun little exercise. I'm just writing down what is trajectory optimization, and then we can think about using this for the next set of tools. Hopefully that looks familiar to you, right? So for the rocket, for example, our cost might be, we want the final, the state of the rocket at the end of our time horizon to have zero velocity and to be at the ground of Earth, right? And then we have some cool rocket dynamics, and then we optimize over all this. So this all works. This works great. How about another one that's awesome? Backflipping robots. So I think Russ has maybe showed you this video before. In the top, Atlas from Boston Dynamics doing a backflip, which is awesome. Or in the bottom, when we said trajectory optimization there, and as some of you may know, it started out as a class project from this class last year, when I TA'd this class last year. Right? And so trajectory optimization totally works for that type of a problem. We can apply that tool. How about flying a quad rotor in an unknown environment? So this is a video from Skydio. This is an amazing autonomous system, right? It's flying around all these trees, identifying where everything is, and then flying very smoothly. So at least for the control part of this problem, again, we can definitely use trajectory optimization. And this is, in this list of problems I'm going through, this is the first one where the perception of the world, not just the robot, starts to become a really hard problem. And so to clarify, we don't really perfectly know the state of the world. We know the state of the robot, but maybe not the state of the world. And so the state of the robot for anything that's rigid and flying is going to be a 12-dimensional thing where we have x, y, z, roll, pitch, yaw, and then those first time derivatives. But then the state of the world might be, in Skydio's case, for example, they have some visualizations of, they do a local voxel map, and it might have 50 meters by 50 meters or so. These things really can become quite huge when a robot starts to be estimating the state of the world. Motion planning for cars. Here's a Waymo car. Again, this is another great potential use of trajectory optimization. For this problem, though, a very hard part starts to become that the world, in the Skydio case, you can basically assume that the world is static. For cars driving around, we can't assume that all the other drivers are static. And arguably the hardest part of the autonomous car problem in 2019 is really reliably predicting what all the other drivers are going to do. There's other hard parts of the problem, too. But for the actual motion planning part, we can use trajectory optimization. So we're talking about manipulation today. You might think, oh, manipulation, I've seen a bunch of robots in factories like painting stuff and welding stuff. That is a type of manipulation, but that's a fully actuated system. And again, different types of motion planning controllers is useful, but we don't think of that as hard of a problem as some of these other ones. So now let's think about general manipulation, where the problem here is we've got some robot and we put some stuff in front of it that it's never seen before, and we say, hey, robot, do something with this. And we might know the joint angles of the robot really well, but what about, what is that shoe that I've never seen before, or that tennis ball, or that pizza? How do I represent the state of that, and what's the dynamics? So as a way to use our brains to think about, really hard manipulation tasks, what even is all this stuff? Russ loves the application of sushi making. I think it's a really interesting, really challenging manipulation task. So I grabbed this video, and as we watch it, let's think about what is the dynamics, what is F, what is the cost function if we were to try and get a robot to do this task, and what is the state, okay? So we'll watch a few different parts and we'll see what you think. So here, he's taking some shrimp or something like that, and he's putting it in some, it's like tempura batter, right? Okay, so what's the state of the tempura batter? You go figure that one out. And then here's some shrimp in a deep fryer, and then you got to decide when to take it out. So what's the state there, right? Is it the yellowness of the shrimp? I don't know. How about here's some rice? So you can instantiate a discrete state, a continuous state for each of the discrete different pieces of rice. But there's like thousands of pieces of rice right there, each with their own, they're each different size too. And then you're going to sprinkle a bunch of seeds all over that? You have to estimate how many seeds there are? Right? Okay, how about this task? How do you write a controller to do this? In the dimension of a human hand, I don't know what it is, but we've got a lot of joints in our hands, right? And that's a very complex thing to do. This one is very fine. He's chopping the avocado just so precisely. And he's clearly sort of using a bunch of tactile feedback to put his fingers right next to the thing, flattens it out. He's got very long horizon motion planning here. He knows what he's doing very far into the future. This is amazing stuff. Okay, so quiz. Who knows what the dynamics was, or the cost function, or the best answer for the state, or even the dimension of the state? Who knows? Francois knows. Francois knows that we don't know. Unless you do know. No, yeah. So this is the point, that these things are very hard. If you want to explicitly represent all those individual grains of rice, you can try, but these are very, very hard problems to try and just directly take kind of the toolbox that we're used to and apply directly. So the point here is that the toolbox you've been learning this class is very directly applicable to a whole bunch of problems, including manipulation in some regimes, and kind of the very general, crazy, robot do anything type of future that I think we will eventually get to, the Rosie the Robot or the Baymax type of robots. It's definitely, there's a bunch of research challenges in applying or extending our toolbox there. So one formalism to think about some of the key differences in manipulation and some of the other application areas is most of what we studied in this class we can think of as being Markov decision processes. And Markov decision processes are usually written with state and actions as S and A, but I'm writing them here in the language that we use, which is X's and U's. So we can define a Markov decision process, some of you might have heard of these before, as a set of a state space, a control space, an input space, the dynamics, F, which is usually called the transition operator in MDPs, and then we can have our cost function, which is usually called rewards in MDPs. So the set of these things together would fully define a Markov decision process. And what that looks like is that we have some state. This is very important. We have some state, and then we have some policy which decides what to do based on our state, and then the two things being the state and the control input then bring us to our next state. And once our next state is defined and we know that state, we can forget everything from before, because now we know our state, we can then we can decide our control policy, and again our dynamics send us to our next state, right? So this is the regime that most of the class has been operating in. For a partially observed Markov decision process, they're called POMDPs, we have a big difference. The big difference is that we don't get to directly observe our state. And I've written it here as y, which is our observation space, and then g, so y equals g of x, we can call it our observation function, which is the thing that is something that it's dependent on the state, but it's what we can actually see. So like I don't know the full state of all the sushi, but I can see something with my eyes, right? And so in a POMDP, we have some state, but we don't get to see the state. All we get to see is just some observation of the state. And then we can magically come up with some control policy, which we'll come back to. Now the control policy and the actual state, which we can't see, those are the things that send us to our next state. And this process repeats. And the difference here is, so I'm going to draw what some of these lines are. In the MDP, it's the dynamics, which is the thing that takes the state and the control input and goes to the next state. In the POMDP, we can also think of it as having a dynamics going from some unknown state and a control input to the next state. But then we also have G is shown, which is the thing that goes from X to Y. And in general, in a POMDP, these are the only things we know, which are control inputs and observations. We don't know G, we don't know F, and we don't know X. And an interesting difference in POMDPs is, as opposed to in MDPs where we can have a totally optimal control policy based only off of the current state, in a POMDP we might want to take our entire history of observations in order to get the best estimate of what we should do for our policy. And in general, in a POMDP, or sometimes in robot manipulation, for example, we don't even know what our cost function should be. So what are some things that might be good ideas to try and do given how hard some of this stuff is? Let's just throw some terms out there. So one is you might want to try and estimate F. That might be useful. And that is what we call system identification, or you can also call it model learning. Might also be a good idea to try and estimate what is the observation function and try and estimate X. And we call that state estimation. You've probably heard that term. One thing that, as Lucas and I were talking about, I don't think people really do this, but in manipulation, we don't even know what the dimensionality or what the general form of the state space often should be. And I guess you could kind of call that sys-ID as well, but I don't really see many people in the field work on that problem, and I think that's a very important and interesting problem. And another one is, if, let's say we don't even have a cost function, how can you come up with a cost function? So taking demonstrations from an expert and using them to estimate your cost function, we call that imitation learning. And so these are, I think, all very relevant to the overall problem of trying to solve general POMDPs. So again, what is hard in general manipulation? We've got unknown dynamics F, unknown objective C, unknown observation function G, unknown state X, and we don't even know what the state space is. Yeah?
Can you go back to last slide? There's just a lot of valid names and things.
Sure. And so, to take our hammer again of trajectory optimization, I'm going to factor one thing here because we do know control input. So I'm just going to say that we've got some like general cost function, but then we also have a quadratic cost on U, right? And in general, for the systems that we like to use this for, does anybody know what form of an optimization problem this is? In general, it's an NLP, nonlinear program, because the dynamics constraint can be nonlinear and the cost can be non-convex, right? So that's why we get local solutions. So in manipulation, though, things are different, right? Because we don't know X in general all the time. And we don't know the dynamics. And we also don't know the cost. So we are left with this problem, which is a quadratic program, and we can solve the global optimality, which is U equals 0, which is the robot does nothing. So this is one of the key problems in just not knowing anything and trying to do something. Definitely a variety of things need to be different in this very general manipulation setting than in more well-known robot settings. So all these different things sysid, state estimation, imitation learning, et cetera. These are all very useful things to do so we can try and fill back out some of the problem. So again, all we have is observations and actions. That's all we got. Okay, given the scenario that robot manipulation is very hard, I think there's 4 options that we have. First option is find problem domains where most things are known. And this is what the field has done a lot of over the years, and there's very good results. Even in domains, as we'll show, where a lot of parts of the problem are known, it's still very, very hard. Because even if you know what the dynamics are, they can be very hybrid, and it can be very hard to do any type of planning or control over hybrid dynamics. Another option is to just assume that some subset of things are known and just do research and hope that people will solve the other parts, and then hope that in general your stuff is applicable later. And I think this is actually a very good route, because I think in research you can't tackle everything at one time, and I think it's good to work in regimes where you just assume that somebody else has solved part of your problem and you focus on one part. I think it's a very good option. Another option is to tackle the hardest general case, which is where we only have observations and actions, and we don't have a cost function or dynamics or anything. And then the other option is to work on different problems. And I think those are the 4 options. So if we think about these things that we may or may not know in different regimes in manipulation, because again, the most general case, we don't know most of them, but we can also work in regimes where we know some. So I think it's very useful to think about what are different types of domains. So the most restrictive one that you can do is you can assume that everything is known and that your dynamics are not complicated. You know X, and you know your cost function. You always know your control input. Another one, which is, again, I think a lot of good research is you might know the dynamics, but they're very complicated because you're pushing something around and it has all these hybrid sliding modes, and it's still a very, very hard problem. Another one is that you can not know your dynamics, and you can still have a good cost function. And Lucas is actually going to talk about this regime later today. So we know our cost function, but we don't know our dynamics, and we're trying to figure out what to do. In a POMDP, which means that the difference with the one above is that we actually don't know X, then we still might have a cost function. Maybe it's a cost function based on a function of our observations, but we don't know X. And in general, this would be a POMDP. Or also, in a POMDP, sometimes you can just magically measure your reward. Think like a video game setting. Like, you don't necessarily need to get to observe the direct state, but you're getting a reward function from the video game. And then, again, the hardest one is you don't even know your cost function, and all you have is observations and actions. And again, Lucas is going to go into more detail on that unknown dynamics domain. So I just want to pause real quick and see if there's any questions so far on kind of the overall setup of what we've been doing in class so far, what you guys have been doing in class so far, and what are the problems in manipulation, yeah?
How would GBUX you're estimating the state, like you don't know the state of everything you're estimating, and you're looking at
No, yeah, so it's a good question. So definitely on an airplane, you have to estimate state. Like, you don't have just some magical thing that just says, here is exactly your velocity and your position in the world and things like that. On an airplane, state estimation is what people do. They estimate the state. You can use what's called pitot tubes to estimate your airspeed velocity. But it's going to be noisy, and so there's a lot of good state estimation work in taking noisy measurements over time and fusing them and getting a good state estimate. So yeah, so when I say that, like, on a plane, we can just know X and we can apply Lyapunov stability analysis, that is including state estimation, yes.
Sorry, I'm more assuming you mentioned that one area is find G inverse.
Yes.
So that we can go over our observations to our states.
Yes.
And in the case of a plane where I design by G, I know G inverse root by definition that I designed by G. But in the case of like I guess manipulating sushi, I don't know by G. So is that question?
Yeah, no, it's so you can model G, right? So you can say that you have some noisy measurements, and there's somehow like a Gaussian distribution on what the true state is. So you can always model it. Same with how dynamics. Like we can always just model dynamics. I'm just basically all I mean to say is that with sushi, state estimation is much more difficult, I think. It's not to say it's not hard on planes. It's also hard on planes, but it's just very hard, I think, with estimating the state of sushi. Any other questions? So I wanted to go through a handful of results and what people have done in manipulation over the years. As far as I know, this is the first, and it's always hard with superlatives in research world, but if it's not the first, it's definitely one of the first few, result where somebody actually took a robot arm and they went to go grab something that they didn't, they actually needed to use computer vision and state estimation to figure out where the thing was. In this case, they knew what the size of the blocks were, but this is way back in 1970, and they were actually using computer vision to decide where are the blocks and then go have the robot hand grab the blocks. And this was back in 1970, and if you look at like a lot of current robot research, you'll see a lot of very similar looking experimental setups. So I think it's a good thing to keep in mind that we have been doing this since 1970, but there's still a lot of challenges. So this one, I just wanted to let this video play. This is from 2009, and there's just a whole ton of amazing results. This is from this Japanese lab doing these very high-speed manipulation tasks. So they have this just amazing hand. This is like super slow-mo right now. You'll see that it's just very, very fast. And just an amazing sort of like overall systems engineering effort with this awesome hand. And then this is their camera setup. They've got this gimbaled camera, active gimbaled camera, where they can track at super high speed some type of thing that they're looking for. Now this type of computer vision pipeline is engineered to look for the thing that they know that they're looking for. They also had tactile sensors in this setup, and they use them for real-time feedback. One of the tasks that they do, which we'll show in a second, is dribbling this ping pong ball super high speed. They also flip these pens around, and they do this throwing. Just amazing stuff at how fast this is reacting to this ball in this case. And they have a pretty good model of what they think it's going to do. It's a thing that's flying around ballistically, but very cool. Another one, very cool, right? Let's see if I can get to the main one I wanted to get to, which is at the end here. Oh, they tie ropes. They grab single grains of rice. I think it'll show it again. Here, it's a single grain of rice. That's very hard. This is the coolest one. Awesome. So they're definitely estimating, what is the state of that phone, and then they go and grab it with a bunch of really high-speed feedback. Very cool stuff. I want to show a couple things from our lab. This is joint work with Lucas, and then the next one too is also joint work both with Lucas and with Wei, one of your TAs. So, different works in manipulation try to address different parts of the problem. And in this one, we tried to address a very low assumption on what is the state space. We don't really have an explicit state space representation. We just do only self-supervision to decide how does the things that we're looking at correspond to things that we've seen before. And so I think we can get some pretty nice, these are class general descriptors, which I can talk more about what they are, but I just want to kind of give you the gist. You can get class general descriptors of different types of objects. And we've never seen some of these objects before, so we've never seen those shoes, but in the visualization on the right, it's showing you that things should generally correspond in this descriptor space representation that we train the vision system to have of how different objects, even if you've never seen them before, correspond. So in terms of what types of tasks that lets us do, that means that we can take one reference object in one image of the class, and then we can just chuck any shoe in front of the robot, and it can identify and grasp the corresponding part of that shoe. And this process would work for, any type of class of objects. And then Lucas was taking off his shoe and checking it on the table. So that was some cool recent work. And again, different parts of the problem we are either addressing or not. In this one, for example, we don't address at all what are the dynamics, right? So we're looking at a static world, and then we go and do something with that static world. Did you have a question? Yep.
Yeah, and then do you tell it, like when you go from like hat to shoe, like you tell it that it's looking for a shoe now, or like what its representation, what it thinks is like the other set of shoes?
Yeah, when we do the shoe version, we change the configuration file to be the shoe one, and when we're doing the hat version, we change it to be the shoe one, or the hat one. We could train it though to do object recognition of which class is which different one, but that's not something we did. Yep.
Did it figure out where on the shoe grab, or you told always grab when you were talking the shoe?
So the cool thing is that we took one image of one shoe, and we just pointed out a part of the shoe, and we could have pointed out any part of the shoe because its trained visual model can correspond any part of any shoe to any part of any other shoe. So just in one image, we say, grab this part. And then the interesting thing is it can then take that and apply that to any shoe. So another example would be if we trained one on cars, we could say, this is what a door handle on a car looks like. And then without it knowing what a door handle on a car looks like, it could just learn to correspond that to every single door handle on every car. That type of a thing. So again though, you can't address everything at once, at least not always. So very much a static world assumption. So because the world's static, the dynamics don't really matter. And then we also can't, in this paper at least, we didn't demonstrate doing anything with the object once we grabbed it. So next paper, which is very much sort of advancing this line of work, but a step further. In this one, we can actually grab objects and then do something purposeful with them. So in this one, we're going to grab a mug, and it can be any mug, even a mug it's never seen before, and it can precisely put it onto a rack like that. And that's just one example, and it worked for all those mugs. This one actually worked 100 out of 100 times in a row on unseen adult-sized mugs. Very, very precise stuff. And the key idea here is we train it, so this one has a little bit of human supervision. We train it to have a general visual representation that is more explicitly 3D and semantic, so then we can have a very general and useful way of specifying what the goal should be. So in this one, you can specify the goal as look at the bottom of the mug and the top of the mug and put the bottom of the mug on the table and the top of the mug above the table. And you can do this task with only 2 key points. And again, those key points in this paper are more explicitly in 3D and trained to be recognized with a little bit of human supervision. So this works in a lot of different cases, and here's just another demo of putting shoes onto a rack. And I thought it was fun when we had a visiting students weekend. Lucas set up a demo, and just anybody was just putting shoes in front of the robot, and it was putting it on the rack. So it works for any shoe, even if it's never seen before. So yeah, again, close to home stuff that I'm excited about, but that'd be cool to show you guys. I did want to do one slide on imitation learning, which I think is very important. And imitation learning is one way to address the case of my robot only has observations and actions, and I need to tell it what to do, right? So one slide on what imitation learning is. I think the best way to think about imitation learning is we have some expert, like let's say that you know how to do sushi. You as a human know how to make sushi. So you have a policy in your brain that somehow takes observations of the world and turns them into action. So you have that policy in your brain. So what we would really like to do is just take the policy out of your brain, download all the parameters of your policy, and put them into the robot. The thing is, we don't know how to do that because we don't know how to download parameters out of your brain. So we'd like to do that, but we can't do that. So the next best thing we can do is we can take a bunch of demonstrations of us using the policy. So we have a data set D, which is a whole bunch of trajectories, where each trajectory is a set of observation-action pairs. You can also do this without actions. You could use just observations. And then we want to use that data set of demonstrations to infer what the policy should be. That's the key thing. And there's generally three different ways to do imitation learning. The first is, I think, the most straightforward, which is behavior cloning, which means you basically just do supervised learning of the history of observation, the history of observations to a control action, right? It's just a supervised learning problem. And there's a lot of subtleties of getting it to work well, but it's pretty straightforward. The second one is more complicated, which is very much a two-step process. The first is to actually infer what the cost function should be. So in behavior cloning, we never know what the cost function is. We just do supervised learning of observations to actions. In inverse optimal control or inverse reinforcement learning, it's called the same thing, we first try to explicitly infer what the cost function is, and then we try to optimize our policy given that cost function. So that, again, we're operating this regime where we don't even have a cost function, but we can take demonstrations, try to infer the cost function, and then optimize that policy. And then the third, in my mind, is really, some people call it a type of inverse reinforcement learning strategy, but in my mind it's really fundamentally different because you don't have an explicit reward function, is generative adversarial imitation learning, where the goal is to just try to make the policy of the learner be indistinguishable from the policy of the expert. And we'd love to go into more details on all these things, but we're doing high level for here. And then Lucas is going to go into more detail on, again, one part of manipulation, or at least one approach. So I've got one more example work for you. This is one type of approach of doing imitation learning, and just a demonstration of the types of things that in this paper they're able to do. This is some really impressive work. In this work, they can just take demonstrations of a human doing a task, which is opening a door. And then this is an IRL approach. So they do try to infer the reward function, although they don't have much to stand on in terms of inferring the reward function. So it's quite interesting that they're able to get something that seems to generalize pretty well. And then I think this paper has really nice sort of actual manipulation results. And pretty efficient in just about 100 trials, the robot is able to actually open that door. And again, this is operating in the setting where it has no known dynamics, no known cost function. All it ever had was observations and actions. And in this case, there's a subtlety in this one. The observations had to solve the embodiment correspondence problem because the observations were from a human doing a task, and it, as the robot, it has a different physical embodiment, and it needed to solve the task. So this is addressing certainly a very, very hard problem. So that was my last slide. Yeah, question?
This is super impressive stuff, and I was wondering if it seems like some of these results could be actually just really awesome algorithms. It could also just be one of the research people expressed about a deadline, just has the robot open the door.
That's right.
Have you ever run into that problem where some results that you see in other papers that look really impressive just aren't replicable?
That definitely happens, yes. I think this paper, I definitely believe the results of what I've showed you. I could easily say what the limitations would be, which is that I think if you just, in this specific one, if you just turn the camera right 90 degrees, it might not work as well. But that's just, this is machine learning, and we need to have a good training set match a good test set. So you could certainly solve that problem by just expanding your training set. But yes, there's definitely a lot of results that go out there that might not work, but I think this is a really nice paper in this case, and the other ones I showed you. I tried to cull. Yeah. Any other questions before we hand over to Lucas? All right, Lucas is up. I'm going to switch mics and stuff a second here.
Yeah, can you hear me now? Yeah, I turned it off for a second to. Which one of these is it, Pete? This one. Yeah.
Yeah, that one didn't take much time.
Okay, so can you all hear me? So Pete gave a great sort of overview of manipulation and how sort of the challenges are a little bit different, especially not knowing the the state space, the dynamics, cost function. Those are all challenging things. So I wanted to go in my part into a little more detail about how you would do sort of a context-rich task, and my part is going to be much more narrow, and it's only going to deal with some of the challenges that Pete talked about, basically only going to deal with basically an unknown dynamics function, which I think is pretty relevant in a lot of cases in manipulation, and show you just one way that you could start to solve the problem. Okay, so what's the challenge? So imagine you want to do something like screw a cap onto a bottle, right? So if you actually think about doing that, right, if you go down and now you're a little bit tilted, think about all the different contact conditions that could arise, right? So like it could either be like the whole rim is making contact with the threads, or it's off-center. There's many different situations that can arise, and it's pretty hard to write down the dynamics for this task. So example tasks are like screwing a cap onto a bottle, even a much simpler task, which is doing peg and hole insertion. So that's a pretty common industrial task. That already has a fair number of contact modes. And if I now change it from being a circular peg, which is what you typically find, to some weirdly shaped, like a star shape or a square, the number of sort of different ways it can be touching, it just blows up. So it gets pretty hard to write down the dynamics pretty quickly. And it can be hard to estimate that contact state, even if you did have the dynamics. So those are big challenges. Okay, so some of my text disappeared. Okay, so how can we go about trying to attack these problems? So I think one, starting from sort of the model-based side, I think how to do feedback control for manipulation in these hybrid settings is very much an area of ongoing research. I think Francois has done great work in that. And I think there's really a lot of positives about this approach. So I think you get controllers that can have really good generalization, because if your model sort of carries over, that can work really well. You don't have to like retrain if you change something. Maybe you can just change one parameter. I think it gives you a lot of insight into the problem. I think on the negative side, it can be really hard to deal with hybrid dynamics. That's a huge challenge, I think, and it's an open area of research. I also think that it's very hard to get started if you don't have the dynamics function. So if you don't have F, it's pretty hard to get started with controls. And also partial observability can be a big problem, which is you can't observe all the components of X. And I mean, that's true in general. Usually you just have some observation and you're doing state estimation, but that can be a big challenge in manipulation settings. Okay, so there's also learning-based approaches. I think these are very popular right now. Like there's tons of work on them, and people like OpenAI and DeepMind are doing them. And then there's a whole slew of them, and Pete talked about sort of one class which is under the umbrella of imitation learning. So we're going to talk about some other ones. So there's a few out there. So there's model-based reinforcement learning. I would almost venture to call that like system identification, and that's one. Another one, so model-based reinforcement learning, is basically saying we're going to like build a model and then try to do something with that model. There's model-free reinforcement learning, which says no models. Let's just directly try to like optimize like our controller parameters. So instead of writing down the dynamics and then deriving the LQR gain matrix, you just try to learn that K matrix. Would be an example. And then you also have imitation learning, which Pete talked about briefly. So we're going to focus on model-based reinforcement learning because I think it provides some insight, and I think it's very related to the techniques you've been learning in this class. Okay, so what does model-based RL look like? So basically, in orange here, you like roll out some policy on the robot or in your simulator. Next, you're going to go and fit a model to what you saw, and that model, we'll talk about what it's going to be, but it can either be a local model or a global model, and then you're somehow going to do some step where you take that model and you get a new policy, a new controller from that. Okay, so those are kind of the three steps that we're just going to repeat over and over again till convergence, and now we're going to go into detail about how each of these works in a specific sort of manipulation example. Okay, so so this is taken from like Sergey Levin and Peter Beal paper, and these are the kind of tasks that we're going to be doing. So the top one here, it's inserting the landing gear of that toy airplane. So it's basically a peg and hole task, and it's got a little rectangular insertion at the end. And then in this bottom one, it's screwing a cap onto a bottle. So this is like the task that we laid out at the beginning. So our goal is going to be to find controllers for doing these tasks. Everything I'm going to talk about today is not going to use vision. So these controllers are actually totally blind. There's extensions for how to use vision. If we have time at the end, I'll talk about that. Okay, so again, as we said, the challenges are the unknown, possibly hybrid dynamics. I mean, in this case, you definitely have hybrid dynamics. And you also have partial and unobserved state. Okay, so basically the rest of the lecture is going to be kind of going over this paper, which I encourage you to read. And I think a lot of the tools we use will be familiar to you. So first we're going to talk about IlQG with known dynamics. So that's basically going to be like LQR almost. LQG stands for linear quadratic Gaussian. It just means you might have stochasticity, but we're not even really going to focus on the stochastic part. Then we're going to see, well, what if we don't know the dynamics? What can we do? And you'll see that it's actually a pretty quick step to make the IlQG with known dynamics and apply those results to the unknown dynamics. So then I want to come back to that peg and hole example, think about that airplane example, and tell you like all these abstract symbols that we've been talking about throughout the class, like what are they in this specific example, right? And then we'll talk about, if we have time, we'll talk about guided policy search, which is sort of a way to convert local policies into global policies. Okay, so this is kind of, we've already talked about, so you just want to accomplish these tasks. So here you can really see the peg and hole task here on the airplane, right? And you actually want a feedback controller. You don't just want, trajectory optimization doesn't give you a feedback controller, right? And it's very unlikely with a peg and hole, which has a pretty small tolerance, that you're going to make open loop trajectory optimization. It's not going to solve the problem in general. So you really do need a feedback controller. Okay, so, and please ask questions and slow me down if I'm going too fast here. I'll try to slow myself down a little bit. Okay, so what's the technical approach going to look like? So basically what we're going to do is, you should think of tau as a trajectory. So when I write tau, so what I mean is a trajectory. So states and actions for some k equals 1 to cap t time steps, okay? So the next thing we're going to do is we're going to say, let's fit a model to these dynamics, right? So as Pete, you can actually see the leftovers of his erased thing. We don't know so we're going to be in discrete time. We don't know this function, okay? So what we're going to do is we're going to do some sort of estimate of this function. Okay? Then we're going to optimize local controllers that optimize against that learned function approximation. Okay? And that's basically going to be done by doing IlQG. And then we're basically going to repeat that over and over until we converge. And I'll show you how that works. And then at the end, I'll show you how to get a global policy from imitating those local policies. Okay, so first let's talk about the easier case, which is IlQG with known dynamics. So basically, I'm going to go through this in a fair amount of detail because I think it's important. So basically, this is an algorithm for deriving locally optimal feedback control of a nonlinear stochastic system. So imagine I start with this system. This happens to be written in continuous time. Omega here is like, it's a Brownian motion. Basically, just think of it as process noise. So how do I solve this problem, right? I want to solve for pi, which is my policy, so my controller. How do I do this? So IlQG, how does it do this? So basically, it's going to convert the problem into something that we do know how to solve. So if we have quadratic objective and linear constraints, then we know how to solve that, right? And we would just use LQR to solve that. So let's try to basically fit this into the LQR framework and see where that gets us. Okay, so basically we're going to start with a current trajectory, so x bar, u bar. What we're going to do is we're going to do an approximation along that trajectory. So we're going to say, let's do a quadratic approximation of the cost locally and a linear approximation of the dynamics locally. So now we have an LQR problem. We can solve that, okay? And that'll give us a controller. And that controller is solving the LQR problem. So that isn't the end of the story. So if our dynamics really were linear and the costs really were quadratic, that would be the end of the story. But this approximation is, we did this approximation to get into that setting. So that's not going to be valid globally. So what we're going to do is we're going to take that controller, apply it from where x bar started, and we'll get a new x bar. And then we'll redo this procedure. So we have the picture you should have in mind is, here's some trajectory through state space. This is like x bar, let's call it 1, u bar 1. So this is what I started with. I solve some LQR, I do my quadratic approximation thing, I get a new controller, and I start it from there, and I say, let me just start there and do what my controller tells me. Maybe that'll give me a slightly different trajectory, okay? So this one is like x bar 2, u bar 2. And then I'll redo the procedure there. So I'm going to be moving locally like that. Does that make sense to everyone? Okay, so we're basically just going to do this a bunch of times. Yeah?
I think a good question to ask is, how come we have to approximate the cost if we know the cost?
Because it may not be quadratic. Yes, sorry. So in the actual example I'll show you about the peg and hole, that cost actually is quadratic, so you don't have to do anything. It's really just to make the cost quadratic if it's not already. A quadratic approximation of a quadratic function is just the function. So, good point, Pete. Okay, so let's talk about how we're going to do this little section, right? So we start with this nominal trajectory. We get a discrete time version of our dynamics. And now we're going to look at relative coordinates to our dynamics, right? So we're going to look at some coordinates which are deviations from this nominal. So here you can see the delta xk notation is just, this is my nominal trajectory. And the nominal trajectory is actually has controls as well, right? So let's just do a local approximation in these coordinates, right? So now I can write down this form here, this delta xk form. So. So does everyone agree this is in the form of linear dynamics now? So this extra term that you're seeing here has to do with the Gaussian noise, but I don't want you to worry too much about that. And we can do basically the same thing to expand the cost. So basically we can approximate the cost basically using terms that are either constants, linears, or quadratic in the delta x's and the delta u's. And this cost function and those dynamics, they fit into the LQR framework, basically. Okay, so now that we have something that fits into the LQR framework, let's actually go ahead and solve that to get a controller out. Okay, so this is very similar to LQR, and I do want to go through a bit of the math here. So basically, you're going to work backwards in time. At the final time, because you've already done a quadratic approximation to the cost, you already know that your cost to go function is quadratic, right? Because the cost to go at the final time is just the instantaneous cost. So now, suppose that, and this is an assumption, we restrict ourselves to controllers that look like this. So we're going to restrict ourselves to controllers of the form so these are linear or affine controllers, okay? So you can show that basically by doing a bit of an expansion, that if you just work backwards, the cost to go, if you use an affine controller, any affine controller, it doesn't need to be the optimal one, then the cost to go will continue to be quadratic. And that's sort of the magic of the linear quadratic setting. Okay, and then basically, how do we find the actual control we want to do? Well, we can basically just minimize the cost to go in the Bellman equation. Okay, so let's do that. So you want to solve for the control law by recursively minimizing the cost to go. So I can write the cost to go at time step k as the immediate cost plus the expectation of the cost at the next state, right? And this is where we're going to use the fact that we already know that the cost to go at the next state is quadratic. So that's going to let us expand out this vk plus 1 term into something that's closed form here. And it's going to be quadratic. So to get from this expression for vk to the one that's on the next slide, there's quite a bit of algebra involved that I'm skipping. Okay, but you get to this expression, okay? And it's pretty messy. But the important thing to know is so pi here is u. That's the thing you're solving for, right? And this is a function that's quadratic in pi, right? All the other terms, they're part of the cost to go, but in terms of doing min pi on this expression, you only care about the pi terms, right? And the key fact, there's some notation here, there's some terms that appeared, these g, little g, big G, and h, and those are just like big sausage terms. But the key fact is those all contain things that are either the cost to go starting from k plus 1 forward, which you already know, or terms that have to do with the running costs and the constraints, which you also already know. So you know everything there. Okay, so now let's minimize this with respect to pi to figure out what our optimal control is. So here what I'm doing is, in terms of minimizing the cost to go, I only care about the terms that have pi in them. So let's just ignore everything else. So that's what you see here at the top. So the cost to go only depends on the control term via this expression, right? And this is a quadratic, right? And we can minimize that closed form, right? If you just take the derivative and set it equal to 0, you can see that this is the optimal control. So if our cost to go really was quadratic and our dynamics really were affine, this would be the end, okay? In practice, and I think this is an important point to make, you can't do that. So in general, you need h to be positive definite for this to make sense, right? Otherwise, you can sort of send that cost to minus infinity by moving u in some direction. Basically, your quadratic function needs to be convex if you wanted to have a well-defined global minimum that's not like minus infinity. And the reason you can get h's that are non-convex is because you're doing an approximation of your cost function, right? It wasn't originally quadratic to start with necessarily. So that's an important thing to keep in mind. And the other thing is that you're doing this is a second order method for minimization, right? So you can move really far. Like delta U can be really big. And you should think about, does that make sense to make a huge step in delta U? Like why might that not make sense?
dynamics wouldn't be linear outside the linear range.
Exactly. So like you did a local linear approximation of your dynamics and you're solving the optimal control under that assumption. So that assumption is only valid locally. So it doesn't make sense to take a huge step to somewhere else where that model might not be valid. So that's a really good point. And that'll be true in this case where we happen to know the dynamics but are doing linear approximation to them. But it'll also be true in the unknown dynamics case. The same sort of insight holds. So it turns out it's okay. If you looked at that term where pi appears, okay, and you looked at the gradient, okay, here this delta UA term, the gradient of that term is g plus g delta x, right? So let me just write it out. So the gradient of that cost to go really is this term, right? So we can always basically modify u by going down the gradient, right? And we can do this for a small epsilon, and this will move us in the right direction. Okay? Does everyone see that? And in general, for any, you can put any positive definite. This is a different H matrix. Let me call it H hat. You can multiply the gradient by any positive definite matrix and you'll still be going downhill. Basically, they only move you within 90 degrees. So basically, the key is that you can't, it doesn't necessarily make sense to do the second order method and go all the way to the global optimum, but you can still improve locally, basically by going down the gradient. So that's what I want you to take away from this. Okay. So now, what do we have? We have a controller, right? So this minus h inverse g plus delta x, or this one, these really do have this form, right? So now, that's a controller. So what do? We use the controller to update the current trajectory, which means, let me redraw this picture. So this is the trajectory we started with, right? We have a controller now, which is of this form, right? So now we're not going to be doing U10 anymore. We're going to be doing U10 plus delta U1, right? And so this, if we keep doing that and we keep running our controller, that's going to give us a different trajectory. So let's call that x bar 1, u bar 1. Okay? So does everyone understand how we got from this solid line to this dashed line? We basically apply the controller that we just derived under the linear quadratic approximation. Okay? And so what the algorithm is going to say is, hopefully that moves us in the right direction in terms of our original nonlinear dynamics, nonlinear cost that we were originally trying to optimize. So now let's do the same thing. Let's do a linear quadratic expansion around here. Let's resolve the IlQG problem, get another controller, and move us. And so maybe that'll move us again, and it'll move us again, and at some point we'll be in some local minimum. We won't be moving anymore. And when that happens, one sec, when that happens, we'll have a locally optimal controller. Note that I say controller, it's not just a nominal trajectory. Yeah?
What if on our next rollout we actually get a higher cost trajectory?
So yeah, good question. So the question was, what if on our next rollout we get a higher cost trajectory? That basically means that you let delta U be too big. You went too far, and you got out of the validity of this local approximation. So how you choose this epsilon term, it's really important. And basically what it's saying is you want your next trajectory under this controller to not be too far from where you currently are. So one way is to do this. Another way is to basically say, you can, when you're doing your optimization, you can enforce some basically distance constraint between how far you're allowed to step. And that's what the machine learning people do, and you'll see that as a KL divergence constraint. So that's just saying don't get too far from where you currently are because your approximation is no longer valid if you do that. Okay. So basically you just keep repeating those, and that'll give you a locally optimal controller. Any questions? Yeah.
Here you have known dynamics and known costs.
Yes.
What's the difference between or advantages of doing IlQG versus trajectory optimization plus LQR?
I think it's pretty similar. Yeah, I mean, if you think about internally, like what a nonlinear optimizer is doing, it's pretty similar, right? Like SQP is very much a quadratic approximation of the cost, linear approximation of the dynamics. It's pretty similar. The reason that this is going to be useful is because, I mean, this is doing trajectory optimization. IlQG, in the case of known dynamics, is a trajectory optimizer. The nice thing is that we're going to see how to extend it to the unknown dynamics case. And because it's very iterative like this, it'll show you basically which samples to take next. Okay, we just said all that. Okay, so the recap is IlQG allows us to compute locally optimal feedback controllers for systems with known but potentially nonlinear dynamics. The way it does it is it computes local linear quadratic approximations to the dynamics and costs that basically allows us to use LQR. Okay, so how do we take that and apply it to problems like this, right? So where did the dynamics come from, right? What is F? It's pretty hard to write down here. Okay, so let's try to tackle that problem. So for this peg and hole problem, let's talk a bit in detail about what is X. Or let's first talk about what is the cost function. So the cost function, in this case, there's no vision. The robot's always holding the airplane in exactly the same place. So you can think of the objective is just get the peg to a specific location. Like you can just say, let me put a point on the end of that peg and just to have a cost from where it currently is to where I want it to be, which is the bottom of the hole, right? That totally defines the task. Do we agree? And it's really a task about getting that thing you're holding in your hand to a given target position. It's a very, very restricted class of manipulation problem. And in this case, it can be, the cost can be well defined in terms of things that you know, like your joint angles, because this is just forward kinematics. So this is a really big restriction on this. And so lots of the problems that Pete talked about were like, we don't even know what we're supposed to be doing. Here you do know what you're supposed to be doing, you just don't know how to do it. So that's a sort of an important caveat here. And there's future work that talks about how to get around that. But I just want to make sure we're all on the same page on that one. Okay, so what's our state vector? So this is the state vector that we're going to use to fit dynamics. It's a bit redundant, but it's going to be easier to fit the dynamics. So it's going to be joint angles and velocities. It's going to be the Cartesian velocity on some points on the manipulated object. So that's basically just saying if I'm holding an object and I define three points that are rigidly attached to that object, if I know where those 3 points are, I know where the object is, because 3 points define the Cartesian frame. It's going to be the vector from those points to where they're supposed to be at the final pose. Okay, and then the previously commanded torque. So this is just straight out of the paper. This is what they decide to use as their X. And they just thought it would work well. It's not like there's some specific procedure for choosing this. Okay, and what's the command going to be? The command is just going to be joint torques. Okay, so how do we do IlQG with unknown dynamics? So basically, we want to extend that IlQG procedure we just saw to the setting where we don't know the dynamics. So how are we going to do that? So what we're going to do is we're going to do this rollout a bunch of times. We're going to collect a bunch of samples, and we're going to fit locally linear models to that. Okay? Once we have those locally linear models, let's run the IlQG procedure. We'll get a new controller. Then let's use that new controller to get ourselves to a new nominal trajectory. We'll run that a few times, refit the dynamics, and keep doing that over and over again. Okay? So just in pictorial form, what does that mean? So run your current controller, collect some samples, fit the dynamics. In this case, they're going to be linear so that we can do IlQG. The improve policy, so P of U conditional on X, think of that as your controller. Okay? How are we going to do that improvement? Well, we're just going to solve the IlQG problem, and then we'll use that to update our nominal trajectory by basically just running that controller. Okay, so how do we fit the dynamics? Basically, it's just linear regression, right? So we're going to restrict ourselves to dynamics that are linear, right? So basically, let me use the same notation. Okay, so these are linear dynamics, right? And this is just, if I have a bunch of samples, right? So xti, xt plus 1, I, and so these are samples from the ith trajectory, right? Like, let me do a bunch of rollouts from the same initial condition. And these are samples. If I have these samples, I have the data I need to train this. This is just linear regression. Do we agree? I don't want to go too much into the details here. It actually is a really, there's a lot of subtleties in the actual implementations of how to do this, and make sure that you sort of get models that are rich but not overfit. And so using a prior can be really helpful. You can kind of use any prior you like. They happen to use a GMM here. I'm not going to get into the details of how that works, but just be aware if you're going to go out and do something like this, that is a very important step, how you do that. Okay, so again, these dynamics are only valid locally. They're time varying, right? So if I think about a contact task like peg and hole, my dynamics when I'm in the air are completely different than my dynamics when I'm touching the table, right? They're completely different. But if I have this time varying thing, then I can have one dynamics there and one dynamics at the next time step that are very different. So this framework can handle, to some extent, discontinuous dynamics, which are the case in contact events. So they have this little quote in the paper. They say that the learned linear models average the dynamics from both sides of a discontinuity. I think this is a subtle point. I'm still working through why this is true or why it's a good idea. But the point is, if you have time-varying dynamics, you can capture discontinuities to some extent. Okay. So what does that actually look like on the robot? So this is actually them doing that procedure, right? They're rolling out, fitting dynamics, solving IlQG, and using that to roll out again. And so you see that, like, it doesn't take them that long to get to something fairly reasonable. They claim it's like 10 minutes of robot interaction time. So this seems to be doing something. So what's a caveat here? What is this? Let's say I start the robot at a different initial condition. Can I use the controller I've learned here to solve the problem or not?
I guess no. Are you learning the dynamics of the robot arm as well? So like you change the condition that you learn the robot arm.
Yes, you are in this case, right? It's all baked in because they only had the joint angles and velocities, right? And this and getting sort of following up on that, it's very much a local method, right? All this stuff is like you're learning a controller, and you would only expect that controller to be valid. You know, let's say this is the trajectory that you ended up with at the end of this, okay? You would only expect that controller to be valid You would only expect it to be valid locally because it's really built on all this linearizing assumption, right? And also, like, even if because it's this time-varying linear, suppose you did start from the same initial condition, but I go in there and hold your arm for like 2 seconds, and then I let you go. It probably won't work either because now, you know, these things are really indexed to time. So they might be wrong, even though you're on the trajectory, you're at the wrong time. So there is a lot of, this works really well, but you are optimizing a local controller here, right? This is for a single initial condition. You can get a controller that works. And you would expect it to be valid locally, okay? So now the question is, so that works really pretty well, and here you can see it doing a few other tasks. So here they do like 5 or 6 different tasks. So here it's just them doing, basically open loop trajectory optimization, and then just following that trajectory. And here what you're seeing is the learned controllers doing that. So again, everything here is just using joint angles. There's no cameras involved. So all the things are pretty much in the same initial conditions. But they can do some pretty difficult tasks, like putting this little wooden ring onto this peg. And it's basically the same algorithm that did all of these. What changed was the cost function, right? Basically the target position changed. So let's skip that. Okay, so remember, we only got a local policy, right? Let's say this is the goal here. If I start you somewhere else, if I start you here, knowing this controller doesn't help you, right? You're sort of too far away. So basically, the approach that they take is, let's run this local procedure from a bunch of different initial conditions, okay? So let's do one from there, and this is a whole IlQG sequence, so we'll get a local controller. Now let's do another one starting from there. Okay, and let's do this a bunch of different times, okay? Let's not cover the space, but let's do a good amount of samples, okay? So now we have a bunch of local controllers from different initial conditions. So how might I convert this into a global controller? Any ideas?
If you get some characterization of how local each controller is, and try to cover the space.
You could, yeah, and then just try to do like a lookup into which controller you're at. So that's definitely one approach. It's pretty hard to characterize what these regions are. In the model-based framework, that's what SOS is trying to do, right? And also distance metric in your state space, like Euclidean distance isn't necessarily like a good indication of what you should do, because, let's say the peg is there and I missed, but I just missed a little bit. I'm not too far in Euclidean space, but maybe I need to go and do something totally different, right? So basically the approach they're going to take is they say, so these policies, let's say the kth policy, it goes from state to action, right? So basically what they're going to do, and there's a bunch of different ones. Let's say this is policy 1, 2, 3, and 4. Let me call it J, because K was our time index. So basically they're going to say, let's just train a global function approximator, okay, to approximate. If I just sampled a point somewhere, I just want it to map X to U. So basically it's just, let's train a global function approximator that can approximate what all these local policies are doing. Does that make sense? So that's just a supervised learning problem now, okay? And that's basically an algorithm called guided policy search. So it's basically, you do this, you identify the model, optimize a controller for locally using IlQG, and then convert all those local controllers into a global controller by basically doing supervised learning, okay? And it's a little more, involved than that, because there's some coupling here. But you need to actually learn things that you can then approximate. But that's basically the idea. And to take it one step further, imagine that at test time, okay, you don't have access to some, or sorry, at test time, you don't have access to some of the information that you had during training time. Let's say during training time, you're like holding the object, and so these cost functions based on distances of known points, like you can write those down. But now let's say that at test time, you're not holding the object, it's just laying on the table or something. What would you do? Well, one thing you can do is, instead of having your learned policy take in state, how about we have it take in observation? Okay, so let's try to mimic a controller that was learned using state. Like these controllers very much use state. And let's try to just make it work just with observations. So they have a follow-on work where basically these are images. Instead of, I mean, it also has the joint angles and stuff, but it doesn't have the target positions. So that's kind of how you convert these local policies into global policies. It's one way to do it. Okay, so that's all I have for today. So I can take any questions, but I hope I give you a snippet of how you can do these tasks. We'll just show what this actually looks like. All right. All right, good.